A study by Ghezelbash published in the Journal of Biomechanics looked at creating a model for the intervertebral disc, specifically for the annulus fibrosus, which when we look at the intervertebral discs, the intervertebral disc is in between the two vertebral bones, and the annulus fibrosus is the collagen portion that creates the outer ring. And what they were looking at was the permanent deformation estimates and then also the failure response. While the article actually says that their model is fairly simple, I didn't find it very simple at all, and that's actually probably because I'm not a biomechanist and I don't have a lot of background in mathematical modeling for this. And so if you want to take a look at the actual variables that they used, I'll put a link so that you can see it. But essentially what they did was they took a bunch of variables that relate to the intervertebral disc, and then they created a model and they compared that to the other literature on deformation of the disc and also failure responses. And what they found was that their model was pretty accurate in being able to produce similar outcomes as some of that other research. And what they found was that at 4,000 newtons of compression, there were permanent deformations of the intervertebral disc, but they didn't see any collagen failure of compressive forces up to 4,500 newtons. And the reason why this kind of information is important is that we actually use some of this information when we're creating programs for low back pain cases, specifically discogenic low back pain cases. For example, we generally don't recommend doing sit-ups anymore, and one of the reasons is because of the compressive forces that we see in the low back with sit-ups. They range somewhere between 3,300 and 3,500 newtons, and with repetition, that could be detrimental to the disc. And so it's actually important for us to actually understand how much load discs can actually tolerate without it being a safety risk. The model in this study actually found 3 different variables that had a substantial effect on spinal stiffness and then also on tissue failure. And those 3 variables were collagen content, collagen type, and then orientation of those fibers. And unfortunately, in clinical practice, it's difficult to be able to assess any of those because you would need a high-powered MRI. But I think it kind of shows us that there might be a lot of variability on what a certain person might be able to tolerate based on how their disc is actually constructed. From a biomechanical standpoint, I learned about Poisson's ratio. And so to explain Poisson's ratio, I'll actually use a band here. And so as we push the band out, the height actually decreases. And so that ratio of the height versus pushing out is Poisson's ratio. And so in this study, they actually used 4.999 as the value for the disc. And when they actually increased it to 4.99999, the compression values actually increased by 174%. And so it's interesting because some of the variables in the disc might have a pretty dramatic change in the compressive values for the disc. For reference, and I had to look this up myself, 0 for Poisson's ratio is actually a cork, and so as you push down on a cork, it actually doesn't expand out to the sides, whereas 0.5 is like rubber or cheese, where as you push down, it's going to push out towards the sides.